Welcome back, students. Today we would be looking at some properties of matrix addition, scalar multiplication and product of matrices. Now there are a list of properties that are shown here. Now these are very important if you were attempting any competitive examinations in your future. So thus we need to pay some attention in understanding these properties. Now first property, let me explain to you. If A and B are two matrices, then if you add A and B together, and that addition is only possible if they are of the same order, then outcome of this addition will also yield a matrix of the same order. Now the best way is to understand is by an illustration. Let me assume that A is a 2 by 2 matrix which has elements as 1, 2, -1 and 3, and the B is also a 2 by 2 matrix. Remember, to add two matrices, they should be of the same order. Now B has got 2, 1, 0, 1. Clearly the order of A is 2 by 2 and the order of B is also 2 by 2. Now if you were to add A with B, then you would get the following: 1, 2, -1, 3 is added with 2, 1, 0, 1, which would in turn become, I add the first element present in the first row with the first element present in the first row of the other matrix. So that would be 1, positive 2. Following it up would give me 2, positive 1, and then -1, positive 0, and then 3, positive 1. So that in turn would be 1 added with 2 would give me 3, 2 added with 1 would give me 3, -1 added with 0 would give me -1. Of course, the last element in that case would be 4. So clearly the order of A plus B is also 2 by 2. So that is what they are saying for the first property. Property number 2, it talks about addition being commutative. Commutative means if you were to add A with B and then repeat the process by adding B with A, then A added with B would be equal to B added with A. We can see the same example. I have already added A with B here. So let me now try adding B to A. So B is 2, 1, 0, 1. Adding it with A, which is 1, 2, -1 and 3. This can be rewritten as 2 added with 1, 2 plus 1, 1 added with 2, 1 plus 2, 0 added with -1, that's going to be 0, -1, and 1 added with 3. This can be rewritten as 3, -1, 3 and 4. If you were to see the matrix of A added with B, the elements are one and the same. So thus this property, matrix addition being commutative, is found to be true by an example. Now moving on, the third property talks about matrix addition being associative in nature. To explain that property, I need to take one more illustrative example for matrix C to be as 1, 1, 0, 0. So now we are going to check if A added with B added with C would give us the same result as A being added with B positive C. Now let me just start off by considering the left hand side first. Okay, in the left hand side we have got A added with B, which we have found as 3, 3, -1 and 4. Now let us see if A added with B being now added to C would result in 3, 3, -1 and 4 being added with C matrix 1, 1, 0, 0, which in turn would give us 3 plus 1, 3 plus 1, -1 plus 0 and 4 plus 0, which is equal to 4, -1, 4 and 4. So A plus B plus C gives me 4, 4, -1 and 4. Now let us continue on by working at the right hand side. Consider the right hand side. Now what we got in the right hand side? First we need to add B with C. So that would mean matrix B, we have matrix B as 2, 1, 0, 1. Now that has to be added with matrix C, which is 1, 1, 0, 0. When we add, we get 2 added with 1, 1 added with 1, 0 added with 0, and 1 added with 0. This in turn would give us 3, 0, 2, and 1. Now it's time to find out what happens when we add A to this output, which is returned as the matrix A. We have taken matrix A to be as 1, 2, negative 1, 3. Is now being added with B positive C, which is 3, 2, 0, 1. Adding, we get 1 added with 3, 1 positive 3, 2 positive 2, negative 1 positive 0, and 3 positive 1, which can be rewritten as 4, negative 1, 4, and 4. Now, this has to be compared with A plus B plus C. Can you see that? This is what we have got. 4, 4, negative 1, 4. So clearly this implies A plus B plus C is equal to A plus of B plus C. So the matrix addition is associative. Okay, now moving on to property number 4, which says A plus 0, which is a null matrix, would give me 0 positive A, which in turn would give me the matrix A. This O, it's actually a null matrix. This matrix is called the additive identity. Shape, or what would be the form of this matrix O? It would be 0, 0, 0, 0. So now what exactly they are telling us is, if we were to add A with the matrix O or 0, then we would be adding 1, 1, negative 1, and 0 with the null matrix 0, 0, 0, 0. It's actually called the additive identity matrix. So this in turn would give us 1 added with 0, 1 added with 0, negative 1 added with 0, 0 added with 0, which in turn can be rewritten as 1, negative 1, 1, and 0, which is actually the matrix A. Now on the contrary, we are going to be finding out what happens when 0 is added with A. So the matrix is 0, 0, 0 added with 1, 1, negative 1, and 0. This can be rewritten as 0 added with 1, 0 added with 1, 0 added with negative 1, and 0 added with 0. This in turn would give us 1, negative 1, 1, and 0, which is also A. Now clearly, if I were to name this as 1 and this as 2, from 1 and 2, we can conclude that A added with 0 is equal to 0 added with A, which in turn is equal to the original matrix A. Okay, let's move on to property number 5. This is called the inverse operation. Okay, negative A is the additive inverse of A. Now A, property number 5, added with negative of A would give me the null matrix, which in turn is nothing but negative of A being added with A. Now let us take the same matrix. So A is 1, 1, negative 1, and 0. Consider A added with the negative of A. Now remember, if A is equal to 1, 1, negative 1, and 0, then the negative of A, which in this case is going to be written as negative 1, positive 1, and 0. So this is going to be negative of A. Now we need to first add A with its negative of A. So that would be A is 1, 1, negative 1, and 0 is now being added with negative of A, which is negative 1, 1, and 0. This can be rewritten as 1, positive of negative 1, 1, positive of negative 1, negative 1, positive of 1, 0, positive of 0. So this can be rewritten as 1, positive of negative 1, that would clearly give me 0, followed by another 0, then a 0 there, followed by a 0. This is actually the null matrix, which is represented as 0 or O. Now let us go and work out the right hand side, which is negative of A being added with A. So you can place the word consider. So negative of A is negative 1, 1, and 0. This is being added with A, which is 1, 1, negative 1, and 0. Rewriting it, we have negative 1 added with 1, negative 1 added with 1, 1 added with -1 and 0 added with 0. So this can be rewritten as -1 added with 1 would give me 0, followed by another 0 there, and a 0 there, and a 0 there, which is the null matrix 0. Now clearly, if you were to name this as 1 and this as 2, you can conclude from 1 and 2 clearly. We see, what do we see? A added with its negative produces a 0, a null matrix, which in turn is also produced with when negative A is added with A. So this is the property that they want us to understand. So that's going to be property number 5. Okay, moving on. Property number 6. That means A positive B is being multiplied with the matrix A would give us A times capital A, which is the matrix, followed by B times capital A. So how are we going to do this? Now let me take the matrix A to be as some element of X, Y, Z, T. Now A positive B, it's scalar in nature, so we can't do anything about that. So let it be as it is. So A positive B when multiplied with A would be rewritten as A positive B multiplied with the matrix A, which is X, Y, Z and T. This can be rewritten A times the matrix X, Y, Z, T plus B times the matrix X, Y, Z, T. But X, Y, Z, T is nothing but our matrix A followed by B times the matrix A, which is nothing but the right hand side. So this is a simple illustration to show how the scalar multiplication works. So conversely, they have the subsequent property that whenever you take a matrix and add it with another matrix and have a scalar multiple, then that would result in that scalar multiple being multiplied individually with the matrix followed by the same scalar multiple individually multiplied with the other matrix, resulting in a property stated in this fashion. To explain this, let me consider A to be X, Y, Z and T, and let B be equal to alpha, beta, gamma and delta. Consider the left hand side. So that would be A times A plus B, which can be rewritten as A times the matrix A and B has to be added. So let me write the matrix. So it's going to be X, Y, Z and T being added with alpha, beta, gamma and delta. Now this can be rewritten as A times X, Y, Z, T plus A times alpha, beta, gamma, delta. But X, Y, Z, T is matrix A followed by alpha, beta, gamma, delta, which is matrix B, which is clearly equal to the right hand side. Okay, we have arrived at property number 7. So to understand this, let us take the matrix A to be as 2, -1, 1 and 1. Now we have a constant B being multiplied to the matrix A. So for this, let us start off by stating, consider the left hand side. We have to multiply the matrix A with a scalar quantity or a constant quantity called as B. So that in turn would give us B times the matrix 2, -1, 1, 1, which can be rewritten as 2 times B, negative B, B, B. Now, therefore, if I were to multiply this quantity which I've got, B times A, with another scalar, A, then the result would be something like this. A being multiplied with the outcome of B times A, which is 2B, negative B, B and B. So clearly, when I multiply A with this matrix, I get 2 times AB, negative AB and then AB followed by another AB. Now, since AB is occurring all through, you see here, AB there and AB here and AB and AB. I can clearly take AB out and write the remaining terms. That would be 2, -1, and 1, and 1. What is this actually? This is nothing but our matrix A with which we started. So this is equal to AB times the matrix A. That is equal to the right hand side. So that is the understanding of this property. Now we got one more property to go. So we have the last part of the property, which is I is actually the identity matrix multiplied with A would in turn give me the matrix A. Now I is usually written as 1, 1, 0, 0. So this is the way we write the identity matrix. Now if I were to take A to be as, say, 2, -1, 1 and -3, let us see if I multiplied with A gives us back the matrix A. So that is the question. Now I is 1, 0, 0, 1. That's the identity matrix. That has to be multiplied with 2, -1, 1 and -3. Now this would give me row multiplied with the column. So that is going to be 1 multiplied with 2 added with 0 multiplied with 1, row with the column, 0 multiplied with 2 added with 1 multiplied with 1. Of course, I'm running out of space, so let me try to squeeze, followed by the row with the column. So that's going to be -1, followed by 0 multiplied by -3. That's going to be +0. The row multiplied with the column, that's going to be 0, and -3 multiplied with +1 would give me -3. So this can be rewritten as 1 multiplied with 2 added with 0 and then 0 added with 1. Of course, we didn't do that expansion there for that side due to constraint in space. It's going to be -1 and -3. Rewriting it, it's going to be 2, 1, -1 and -3, which is nothing but our matrix A. So that is what the property I multiplied with A would give us back the matrix A. Now the same case is also true when you have the null matrix multiplied with the matrix A. The output would also be a null matrix. So this can be easily seen if we were to represent this matrix as 0, 0, 0, 0. And the matrix A as 2, -1, 1 and -3, then clearly 0 times A would be 0, 0, 0, 0 multiplied with the matrix 2, -1, 1 and -3, which in turn would be taking the row with the column 0 times 2 added with 0 times 1. Similarly, the row with the column 0 times 2 added with 0 times 1. Row with the column, you get 0 times -1 added with 0 times -3. The row with the column, 0 times -1 added with 0 times -3, which in turn was going to be 0, 0, 0, 0, which is equal to the null matrix 0. So thus we have verified all of these properties listed here.